Hello everyone, this is chapter 2.3 and in this lecture we're specifically going to focus on the applications of IR spectroscopy in identifying specific bonds and therefore functional groups in organic molecules. There is only one video for this lecture. So now that you understand the physical basis of IR spectroscopy, we'll be paying particular attention to the bond vibrations that are highlighted in the learning outcome. You're more than welcome to pause the video and read these, and as usual they can be found in your handout. This slide will move on after 5 seconds. So let's have a look at some features of an IR spectrum before we get into the nitty-gritty about the functional groups and specific stretches. So the first thing that you should note about the IR spectrum presented for vanillin is the x-axis. This is given in wave numbers, and wave numbers are wavelengths per unit distance, typically inverse centimeters. This is synonymous with spatial frequency. One oddity about the x-axis that might strike you is that the high energy, high wave numbers are on the left and the low energy, low wave numbers are on the right. The scale is typically from 500 to 4000 inverse centimeters. However, if you were to convert the wave numbers to wavelengths as you see at the top, you can see that the scale is correct. It's just that the wave numbers are easier to cite when they're in this unit. The inverted display of absorption compared with UV-Vis spectra is characteristic also of IR spectra. Thus, a sample that did not absorb at all would record a horizontal line at 100% transmittance. That's at the top of the chart. This means that molecules will often have bonds that either have weak, medium, or strong absorbances. These are often associated with stretching or bending of bonds, as seen in the previous video. The strong band covers most of the y-axis, a medium band falls to about half of the y-axis, and a weak band will fall to about 1/3 or less of the y-axis. There are 4 regions of an IR spectrum that correlate to the energies that produce bond vibrations. Now, by bond vibration, we mean stretching, we could mean twisting. There are some options on display here. Now, not all covalent bonds display bands in an IR spectrum. Only polar bonds do so, and we refer to these polar bonds as being IR active. The intensity of the band, that's the strong, medium or weak absorbance, will depend on the magnitude of the dipole moment associated with the bond in question. So a strongly polar bond like the carbonyl groups produce strong bands. Medium polarity bonds and asymmetric bonds will also produce medium bands, and weakly polar bonds or symmetric bonds produce either weak or they don't produce any bands at all, i.e. they're non-observable. The first region corresponds to atoms that are bonded to light atoms. These are typically carbon-hydrogen, nitrogen-hydrogen, and oxygen-hydrogen bonds. These are also typically single bonds. However, if you remember, we said that shorter bonds require more energy to vibrate, and so it is usually easy to spot, say, triple bonded groups in that region. The nitrile group, which was the carbon that's triple bonded to nitrogen, is one such example of this group, as is the carbon-carbon triple bond found in alkynes. However, alkyne triple bond stretches may be absent if a molecule is symmetrical. Double bonds are the next highest bond strength, and single bonds connected to different atoms fall in a region known as the fingerprint region. Why is this called the fingerprint region? Let's take a look. The fingerprint region, as you probably imagined, is unique to every single organic molecule, and so it's impossible to interpret because of the complexity of the types of vibrations found in this region. Now, if you have a computer database that already has the fingerprint regions of all of the known organic molecules, then this will make your life easier. as we'll see on the next slide. If we look at these very two similar ketones, that cyclohexanone and cyclopentanone, they would be very hard to differentiate just on the basis of their carbon, hydrogen and carbonyl stretches. However, if the fingerprint region with its complicated stretches is compared to a computerized spectral database, only then could these two molecules be differentiated by those stretches. IR just doesn't provide enough detailed information or proof of molecular formula or structure. What it does is it provides ideas about molecular fragments, specifically functional groups. Now, on its own, it's very limited in its scope and is often used in conjunction with other techniques that provide a more complete picture of the molecular structure. Nonetheless, it can be useful for monitoring reactions or part of the characterization strategy for an unknown molecule. So a final note on the fingerprint spectrum: this is the complex area that shows many bands frequently overlapping each other. Now, this complexity limits its use to that of a fingerprint, and you should be ignoring this when analyzing the spectrum. As a student, you should focus your analysis on the rest of the spectrum. That is to the region that is to the left of the 1400 or 1500 wave numbers. That said, carbon-oxygen single bonds can be found in this area, and they can be quoted to support evidence of alcohols or carboxylic acids. Don't worry, we're going to get lots of practice. On this slide, there is a correlation table that you'll be using for infrared spectroscopy. And no one's going to expect you to memorize any of the functional group absorptions, so you'll be provided with a data table like this in any exam. The best approach is to start from the left and work towards the right in this case. For the most part, you can always assume the presence of an aliphatic, that's a carbon-hydrogen stretch, between 2850 and 3000 wave numbers, and this is usually strong. Now, if this bond absorption seems to be weak, this is usually indicative of a carbon-hydrogen with other hybridizations of that carbon. And as with anything, it's going to take practice. You should always have the data sheet that you were provided with from Canvas, and you're probably going to need this for the next part of the video. So please pause the video and load this or get your paper copy. The slide will change after the next 5 seconds. So what I'm going to do is I'm going to take you through each of the IR spectra like what we did for the functional groups. Our first representative family are the hydrocarbons, and these provide us with some very simple IR spectra, particularly for the alkanes. Now, an alkane doesn't have a functional group, and so the only bond stretches will be carbon-carbon single bonds and sp3 carbon-hydrogen vibrations. And of the most useful will be the carbon-hydrogen bands, which typically appear around 3000 wave numbers. Now, since most organic molecules will contain these bands, an organic molecule with this in its spectrum is not diagnostic. In fact, if you see other carbon-hydrogen bond stretches, then that's when you should cite them, because they're indicative of other functional groups. And as usual, please don't cite any of the bond vibrations in the fingerprint region. Here's an IR spectrum of a representative alkene. This is 1-hexene. Now, there will also, as we've said, be an sp3 carbon-hydrogen bands, as shown here, but there's also now an additional sharp medium band that corresponds to the carbon-carbon double bond stretching vibration at about 1600 to 1700 wave numbers. And some alkenes might also show a band for the sp2 carbon-hydrogen bond stretch, and this appears for this molecule at about 3080 wave numbers, as shown here. On this slide we have two types of alkyne. One is a terminal alkyne, where the carbon-carbon triple bond is at the end of the molecule, or the start of the molecule. And we also have a symmetrical alkyne, whereby this is known as an internal alkyne, and this is 4-octine in spectrum B. The most prominent band in alkynes corresponds to the carbon-carbon triple bond, and it shows as a sharp but weak band at about 2100 wave numbers. The reason it's weak is because the triple bond is not very polar. In some cases, such as in highly symmetrical alkynes, it may not show at all, so we can note the absence of this in 4-octine. Terminal alkynes, that's to say that those where the triple bond is at the end or the start of a carbon chain, have carbon-hydrogen bonds involving the sp carbon. So this is the carbon that forms part of the triple bond. Therefore, there may also be a sharp, weak band at about 3300 wave numbers that corresponds to the carbon-hydrogen stretch. Internal alkynes, such as that of 4-octine, will not have the sp carbon-hydrogen bond stretch and therefore lacks this aforementioned band. In a manner very similar to alkynes, nitriles, that's carbons that are triply bonded to nitrogen, also feature a prominent band around 2250 wave numbers. This band has a sharp pointed shape just like the alkyne carbon-carbon triple bond, but because the carbon-nitrogen triple bond is more polar, this band is stronger than in the corresponding alkyne carbon-carbon triple bond stretch. Here is an IR spectrum of an alcohol. This is 1-butanol. The most prominent band in alcohols is due to the OH single bond stretch, and it appears as a strong but broad band covering a range of absorptions between 3000 and 3700 wave numbers. The sheer size and broad shape of the band dominate the IR spectrum and make it hard to miss. They also will contain carbon-oxygen single bond stretches, but these can be a little unreliable and it's hard to know which one is actually characterized as the carbon-oxygen stretch because it falls in the fingerprint region. Next we have the IR spectra of amines, and the most characteristic band in the amine is due to the nitrogen-hydrogen bond stretch, and it appears as a weak to medium but somewhat broad band, but not as broad as the OH stretch band of alcohols. Now this band is positioned at the left of the spectrum and is in the range of about 3200 to 3600 wave numbers. Primary amines will have 2 NH bonds, therefore they typically show 2 spikes that make this band resemble a molar tooth. Secondary amines will only have 1 nitrogen-hydrogen bond stretch, which makes them show only 1 spike, and this represents a canine tooth. Finally, of course, tertiary amines have no nitrogen-hydrogen bond absorptions, and therefore this band is absent from the IR spectrum altogether. So what type of amine do you think is shown here? Pause the video and resume when you're ready. So seeing as we only see 1 spike between the 3200-3600 wave number region and it resembles a canine tooth, then this is actually the secondary amine. We're now going to survey some carbonyl containing compounds. So these are ones that include the carbon-oxygen double bond. So in an aldehyde, the carbonyl bond is found at the end of a carbon chain, whereas a ketone it's found somewhere in the middle, or certainly not at the end. As a result, the carbon of the carbonyl bond in an aldehyde is also bonded to another carbon and a hydrogen, whereas the same carbon in the ketone would be bonded to 2 other carbons. Aldehydes and ketones both show strong, prominent state-shaped bands around the 1710-1720 wave number mark, which is about slap bang in the centre of the spectrum. Now this band is due to the highly polar carbonyl bond, and because of its position, shape and size it's really quite hard to miss. Aldehydes, however, are different to ketones because of course they contain an additional carbon-hydrogen bond to that sp2 carbon of the carbonyl bond. So this means they show a pair of medium strength bands positioned around 2700 and 2800 wave numbers, which is different to the ketone that you see underneath. Those bands are missing in the spectrum of the ketone because that sp2 carbon of that ketone will lack the carbon-hydrogen bond. And this is what allows you to make a differentiation between aldehydes and other carbonyl-containing compounds. So the other type of carbonyl-containing compounds are carboxylic acids, and these contain two different bond stretches. So they contain a feature that is common to the alcohol and that is common to ketones because it has both the OH bond and the carbonyl bond. Therefore, a carboxylic acid shows a very strong and broad band covering a wide range between 2800 and 3500 for the OH stretch, and at the same time they will also show that stake-shaped band in the middle of the spectrum at a lower wave number, which is around 1710 for the corresponding carbonyl bond stretch. The final functional group under consideration that contains the carbonyl bond stretch are that of the amides. The amides will contain nitrogen-hydrogen bond stretches as well as the carbonyl bond stretch. And the carbonyl bond stretch is typically at a lower wave number than other carbonyl bonds, and this you can see in your data table. But what makes this easy to recognize as a primary amide is that molar tooth appearance between 3200 and 3600 that corresponds to nitrogen-hydrogen bond stretch. And if you remember, if it was a secondary amide, there would only be one of these peaks which represent a canine